Hi and welcome. We are Team BioSphere. My name is Teng Ao. My other teammates are Matthew Newmer, Brandon Warman, and Diani B. Ham. Our mentor is Melissa Rose. Our project is sponsored by Dr. Christopher Doty and Jenna Keeney. They work for NAU's Megabiota Lab, where they study megafauna such as animals that live in Africa. To begin with a little bit introduction, tropical forests are vital to the global ecosystem, and environmental problems will never be overestimated. Our clients are focusing on using high-precision data from satellites and processing it to data products for ecologists to locate specific plants and animals in mid-Africa. Their goal is to use the information to help policymakers set up different strategies and policies to do with forest protection and preservation in the mid-Africa area. And for the problem statement part, our clients face a difficult challenge when it comes to interpreting the raw JEDI data that is given to them. The precise data from JEDI, which is a full waveform LiDAR and has the highest resolution and densest sampling of any LiDARs. It was launched to the International Space Station by NASA in December 2018 and completed initial orbit checkout in April 2019. Moreover, the laser radar of JEDI can make detailed measurements of canopy height, canopy vertical structure, and surface elevation. Canopy height is one of the most important factors affecting forest carbon storage, vegetation quality, and biodiversity. It is also the key process such as biomass allocation. As a result, if the data can be easy to view and use, it could be really helpful for our sponsor and ecologists to draw conclusions about tropical forests. However, the JEDI data is difficult to read, analyze, obtain, and visualize, as it contains an incoherent list of numbers that present latitude, longitude, and other different values. As the figure shows, we cannot directly get the specific data product without using any programming tools. Also, our sponsor works with these groups in Africa and has cooperation with other researchers and ecologists. They are not major in computer science, and they cannot handle the data to draw conclusions. It is too hard for them to deal with the raw data. And currently, our sponsor utilizes the Google Earth engine to analyze the data. But this software has proven difficult to use for our clients and has not given them the required tool sets they need to analyze the data easily. And it is not able to use it offline if the user is in the tropical forest. This is where our teams come in. We have been tasked with creating an Android application called Biomapper, which will act as data visualization tool for our clients. In order to make the application that will best help for our clients, we have decided to focus on 5 main functionalities for the application. These functionalities include a base map, action menu, filtering map data, download maps, and the French mode. For the base map functionality, we have 3 features we want to implement. These include displaying a map detailing a specific location, user interaction features like scrolling, zooming in, and zooming out, and having the ability to display different map types based on different data. The action menu functionality will contain preferences, functionality setting, and an about page. The filtering map data functionality will allow our user to input map value that they want to look at, such as setting the minimum and maximum canopy height value of the base map. The download maps functionality allows our user to download a selected region of interest to internal or external storage for offline use. If the offline mode is switched on, the application will automatically view the downloaded maps in the base map interface. Finally, our clients have often collaborated with French speakers, so a multi-language functionality for our application was necessary for them. The application will be able to switch from English and French in the action menu. In order to accomplish these features, Biomapper needs to have access to phone's GPS as well as secured server for the map data and region interested maps to be stored in. The application interface looks like the right two figures shows.
Before jumping into the specifics, we need to address at a high level how we want to accomplish our requirements. Our Android app is being developed using Java within Android Studio. This is because we are more familiar with Java than the alternative language Kotlin. The app relies on the Google Maps platform for displaying our custom maps. However, the data we need to display is too large to be included with the Android app. So, we decided to use an AWS server for receiving HTTP requests from the app and responding with what are known as map tiles. Additionally, if the user wants to filter these tiles to only show a specific range of data values, a Node server handles this. It runs a Python script to accomplish the filter. We chose these technologies because Node is relatively fast, and we are already familiar with using Python for image processing. Looking closer at our Android app's implementation, we can break it down into separate functional modules. As was mentioned, the map itself is made possible through the use of Google Maps software development kit for Android. This allows the user to scroll and zoom the map. The user can choose what data type is shown on the map, and this selection is saved in persistent storage known as preferences. This makes it so the user's choice is remembered next time the app is open. The next functionality to cover is data filtering. The user can apply filters to any of the available 3 data types so that only a limited range of values is shown. This service relies on the API calls to our server and also uses preferences to store the user's filters. One of the most important functionalities is the ability to store maps for offline use. This will allow forest ecologists to use the app in the field without an internet connection. To do this, the user selects a region of interest on the map and then inputs the desired radius for downloading. Once again, preferences are used to store the coordinates of this location and the radius. The downloaded map tiles are kept in the device's internal storage that's specific to the Biomapper app. Finally, we've made use of an existing technology to make the app display its text in French. When Android runs an app, it tries to use a string resource file that corresponds to the device's default language. So we have included a resource file that contains French translations for all the in-app text.
Within the AWS server is a Node server, which acts as an intermediary between the Android application and the AWS server. The Node server actively listens for HTTP requests from the Android application through an API. The API is looking for information like the type of data, such as DEM, CHM, AGB, the zoom level, X and Y coordinates, and height. The API will then search for that tile on the AWS server. From there, it calls a custom Python script that will filter the tile to get the correct color for the height in meters and returns that tile back to the Android app. I'm going to hand it over to Tang to discuss some of our challenges.
The current challenge we are having with the Android application development is to determine which map tiles to download and save them to internal or external storage. The resolution plan for it is that we will set the center coordinates from the user's click and use radius to set the region of interested area, then download all zoom levels map tile to the target folder. The map tiles from each level will cover the area that's the user input. It will secure the selected area from each zoom level be covered by map tiles and downloaded to the phone folder for offline use.
Currently, our team has been making great progress towards completing our goals on time. One small setback we face is not having access to one of our required data sets. We are expecting to have access to this next week after it becomes publicly available. The focus for the upcoming weeks will be on the offline functionality for the Android application, including finishing the region of interest component that will be combined with our downloading tool. We will also need to compile a list of words in our app to send to our client for translation. Once we have this, our multilingual support will be completed. With the server being mostly completed and only needing small modifications in the future, our team plans to divide into two groups. One which will be focused on finalizing the Android application, and the other will begin research and development of the iOS application. In conclusion, the loss of tropical forest is a cause for global concern. Crucial LiDAR data, such as above-ground biomass, canopy height, and digital elevation models, provide insights on an ecosystem's health and biodiversity. The problem is that these JEDI data sets often aren't easy to access and are complicated to understand. Our solution to this problem is providing a mobile app that can download and filter these data sets for offline use, providing in-field researchers with a tool to aid in their research. Over the past few weeks, our team has made great progress towards completing the Android application, and we're only waiting on a few features to be put together. We are looking forward to completing this and moving on to our iOS version soon. This concludes our presentation. Thank you for your time.